everyone. I hope you can hear me. Welcome to this webinar, which is being organized by GMOA. I'm really thankful that they've given me an opportunity in this platform to do this, conduct this webinar.
Good morning, Petson, and good morning, Chief Engineer Desmond. And I welcome all the GMOA members who have registered now for today's webinar. Today's webinar is based on gas carriers, various.
Bhaskar, you are unmute. Mute your.
Good morning, everybody. I welcome Chief Engineer Desmond, Superintendent Engineer, and Chief Engineer Petson, who are coordinating this webinar for gas carriers today, webinar on gas carriers. Chief Engineer Desmond, I will give a brief introduction to everybody. Chief Engineer Desmond Fernandez, who has worked on various gas carriers for the past 15 years, is an IMS student, pass out, and presently is working as a superintendent. He worked on as a cargo engineer or LNG and gas carriers chief engineer, and now taking the role of superintendent engineer. So without further delay, let me hand over to Chief Engineer Desmond, and we look forward to a valuable informative session on gas carriers. Thank you. Take over, please.
Thank you, Bhaskar Bab. Thank you for your kind introduction. So let us start with our presentation. Okay, so what are we going to do here? As the title basically tells you about introduction to gas carriers. So here basically we will understand what a gas carrier is, what this gas carrier is designed to carry, how it carries the cargo, what sets a gas carrier apart from other types of tankers, say oil tanker or a chemical tanker. And then we'll just touch upon this cargo hazards, characteristics, okay. And some of these cargoes which we'll be mentioning, they are being lined up as a fuel for propulsion of the ship. So we will just briefly touch on all those topics. So we'll understand now what a gas carrier is all about, right? So to tell gas carrier in a very simple words, it is a ship which can carry gas as its cargo. Now let's make it a little bit complicated. Okay, this is a definition basically comes from IGC code, which we'll look into understand what IGC code in the later part of the presentation. But this is a definition which basically comes from IGC code, and this is the authentic one, right? So here they're talking about a ship regardless of size. So it can be a very small ship, 10 meters also. If it is designed to carry gas as a cargo, it becomes a gas carrier, right? Second part of it is, in the definition you will find, is liquefied gases. So as you must be knowing, okay, different states are solid state, liquid state, and gaseous state. Gases belong to the gaseous state, but this we basically liquefy it, make it in a liquid form, and then we carry. We will understand why we are doing so in the later slides. I'll attend to that. But more importantly, how the definition points out to this vapor pressure exceeding 2.8 bars absolute at a temperature of 37.8 degrees Celsius. So this is something that we will basically identify, understand how it is. Okay, going to the temperature part, 37.8 degrees basically finds its origin to basically the non-IS standards. Okay, so initially when they were grading fuel and everything, so 100 degree Fahrenheit was what was used as a reference point, okay, for all the fuels, correct? And basically 100 degree Fahrenheit is equal to 37.8 degrees Celsius. So this definition has been given into SI units for us. So it basically talks about read vapor pressure of okay of basically a industrial standard test which has to be conducted. Okay, basically meeting non-viscous hydrocarbon liquids, okay, specified by the Institute of Petroleum Test Procedures, IP 69. So that is the origin. So as you we go to the back to the basics, if we take the gas and liquefy, it will try to revert to its original state, that is the gaseous form. Okay, so if we imagine a tank wherein you have this liquid gas at a temperature of 37.8, so part of it will basically try to revert itself into its vapor state in a gaseous form. This gaseous form will continue until there is a saturation. So there will no more basically more conversion of this liquid into gas happens in the vapor chamber on top of the liquid within the tank. Okay, so as this vapor generates, it basically volume is that limited. Okay, volume is not changing above the liquid within the tank, so that will only manifest itself into rise in pressure. So this pressure basically is measured, okay, and it has to exceed 2.8 bar. Only when it satisfies this condition we call it as liquefied gases. Okay, and all these gases have been listed out in chapter 19 of IGC code. So you will find all everything is being listed. Okay, so that is what this means, and this is something basic. This is a foundation which we are basically building up upon to understand about gas carriers. So these are the significance of it. I would point out that any questions you have, just put in the chat. I will address at the end of the presentation any questions that you have, okay, during the our query session. So some doubts comes to you, please put in the chat and we will take it up. Okay, moving on. We will understand now what those gases are. Okay, here I have just identified very few. There are a lot of close to about 100, I think so, listed in chapter 19. Quantity shift is very less, and similarly VCM or vinyl chloride monomer, all these are basically used in the chemical industry. When we look into other gases, you have nitrogen, which is basically a inerting gas which is used. Carbon dioxide is used in the food industry. They were dedicated, say, 2000 cubic, about four um gas carriers dedicatedly built to carry carbon dioxide, and basically in the Europe. But now it has come into more prominence because of our IMO direction, okay, to capture all this CO2, and then now we want to basically pump all this CO2 back into air pockets which we have harvested, no, for the crude oil and all, and we are storing it. So now larger and larger gas carriers basically to handle to transport this carbon dioxides are coming. So it is coming into a forefront. Okay, the smaller vessels were there, but now larger vessels are being designed, built, recently being started operations also. Refrigeration gases were also used, were carried from gas carriers in limited quantities. And we'll move on to hydrogen. Now this is another thing which is coming up. Now we will touch upon LNG, LPG, all this ammonia, methanol, all those things. All everything is basically transient in nature. Okay, so but then the fuels which of the future which will be prominent is most likely hydrogen and nuclear. Okay, so how like we have all this VLFO, so HFO, MDO, that we are basically predominant, the share of the is much larger. So you will find hydrogen and nuclear which basically is coming into the picture. Okay, these are all into trial phases at the moment. Okay, and I will talk about that interim measure later on. Okay, I will visit that particular part later on. So these are some of the gases which uh, 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 basically transported on gas carriers, and few gases which will dominate in the near future. So in the definition we said that regardless of size, we also said liquefied gas. So now that is what we have to understand. What is this liquefied gas? Why we have to take? Why is it necessary that we have to liquefy this gas? Okay. So when we talk about ship is only a part of the tool in the logistics. Ship we are using to basically transport something. In case of gas carriers, it is the gases which we transport. So the main part over here, it is part of a logistic chain which we have to understand. And when we talk about logistics chain, it is a more of a commercial thing which basically comes. And the basic and the golden rule is economic of scale. This economic of scale has influenced shipping in a very drastic measure. Over a period of time, if you see the trend, ships are getting larger and larger. Why is it so? Because of economic of scale. So similarly, how it becomes economical to carry these gases between different ports. Okay, basically a production location, and one is a consumer. That is what basically derives this market, controls this market. Okay, to understand that, we have to understand the characteristic of these gases. Okay, so here we have to understand, if we uh, change from gaseous state to a liquid state, the volume basically increases. Okay, by 600%, by 259%, by 220%. Everything depends on the type of gas, and that is where the economic of scale. So let me put it in a simple manner. We take for example, natural gas, methane. We will take an example of methane. If we take a container of 1.05 cubic, okay, and we put 1 cubic of gas. Now this decimal zero 0.05 is because regulation requires that we should not fill a compartment 100%. So there has to be little bit of a vapor space. Okay, so we put one. So you can just imagine now 600 cubics, so the size. Okay, but if we convert this methane into a liquid form, then 600 times we can accommodate in this only 1 cubic. Okay, so that is what helps us. So again, what economic of scale. So that has prompted us to basically change the state from gaseous to liquid for the transportation phase, for the storage, because for limited space we can basically accommodate more of that particular gas. Okay, so propane basically it works out to 259 times, butane about 220 times. Okay, these are approx values. Okay, so that basically comes. Now if we have to liquefy the gas, okay, how we can do so? So one is basically we can pressurize the gas. Okay, if we raise the pressure, it will basically change into a liquid form, or we can cool it or refrigerate the gas. Okay, and then again it changes its state into a liquid form, or we can have a combination of the two. We can raise slightly, partially the pressure, at the same time we cool also, and we can get the same results, that is gas in a liquid form. So this is very important because this is another question that basically in our orals being asked, type of gas carriers. So this is the source. Okay, so we have three different categories of gas carriers. We have fully pressurized gas carriers, we have fully refrigerated gas carriers, and those ships which basically utilize a combination of those are known as semi-refrigerated gas carriers. Okay, fully pressurized gas carriers and fully refrigerated gas carriers are very straightforward. More complication comes in semi-refrigerated ones. If you see specifications, shapes, or sometimes advertisements by in the basically for recruitment and all, sometimes it is mentioned as semi pressurized fully refrigerated. So what it means is that it can basically carry certain types of gases in a fully refrigerated state, so it is equal to that fully refrigerated gas carrier, but it can also accommodate higher pressures. So main advantage of this is the number of cargo that the ship is designed to carry increases basis on what pressure and what temperatures it is designed to carry. Okay, and it is built to carry. So I hope if a survey asks you different types of gas carriers, so you'll be able to tell them that it is like fully pressurized, fully refrigerated, and semi-refrigerated, semi pressure gas carriers. Okay, and why is it so? It is only on condition of carriage. Whichever cargo it is designed to carry, in what condition it is going to carry, that determines the type of carrier. Okay, here I want to touch another thing. Some ships, okay, some gas carriers basically will only designed to carry one cargo. Some ships multiple types of cargo. Okay, so that varies, and here that's where little bit complication comes into the picture, but I will touch into it so that particular concept also will get cleared of yours. Right. So we will just try to understand what is this fully pressurized gas carriers and things are. Okay. Okay. Moving on. We will try to understand now what is a pressurized gas carrier. So the picture which you are looking at, this is a typical pressurized gas carrier. Okay, it has about 2 tanks, sometimes 3 tanks also. Capacity goes to about, say, even close to about 9,000 max. These are basically coasters. Coasters mean feeder vessels. In estuaries, rivers, and all, it will go. It does the last mile of transport. Okay, it basically carries in the pressurized form. So the pressures are basically 17.5 bar to about 20 bar, depending on what they are designed at. The tanks basically are equivalent to your air bottles to those 17.5 20 bar pressures. Okay, so obviously capacities are quite less, because what you will find over here, there's a like the thickness of the material is more, so corresponding weight is also more. The temperatures that it can handle, these are designed are typically at 0 degrees. Okay, but it can handle while loading to minus 10 degrees also. So you cannot load a gas over here below minus 10 degrees, so that is which is very important. Now these tanks basically are independent tanks. I will touch upon the tanks, then you will have more clarity into it. At the moment I'll just say these are type C tanks. Okay, just remember independent type C tanks which are basically installed on those. Okay, and these are basically very simple. Whatever rest of the things you will which you will see, I will basically address all those parts in the later slides. So there is another variation. This is something new which has come. Okay, because the market demanded it. Typically the previous ones you will find, and those basically will carry LPG, that is, as I've said, propane and butane. It could carry a little bit of ammonia also if required, but the pressures were a little bit higher. I will touch upon it later on. Okay, VCMs were some of the cargoes that it will carry. Now it also necessitated demand was there for natural gas, and now this is a fully refrigerated ship. So basically, how we are liquefying it by increasing pressure, so compressed. That's why CNG, okay, compressed natural gas. Although now in the compressed state it becomes in liquid form, but we don't call it as LNG, because when we talk about LNG, we basically use refrigeration as a method. Okay, CNG also it is in liquid form, LNG also it is in liquid form, but the way we get it liquefied are different. This is basically by raising pressure for CNG. LNG it is by cooling or refrigeration, that is what we use. So over here, as you can see, temperatures goes down to minus 29 degrees. There we had seen normally 0 degrees is what it is designed for. It normally takes carries ambient. Okay, in the previous one, right, ambient temperature, that is what whatever 38 40 degrees, which varies basically, and minimum minus 10. Here minus 29 degrees, and the pressure also goes up to minus 130 bar to 250 bar. Okay, this is much higher, much higher than what we were talking at 17.5 bar. So these are basically specifically designed only for this. So as I have mentioned, ships can be designed for specific ones. So you have, so these are the two types of in the market that you will be able to see a pressurized ships. Okay, and then let us understand about semi pressurized. Okay, this looks similar to your fully pressurized tank, but then it becomes little bit complicated. Those were relatively simple. So here you will find another basically compartment on the deck, which you can see right over here. Just forward of your accommodation, you will find another tank also, white color in the forward. Okay, we will touch what those are and all. So these basically this type of ships you will find close to about 20,000 cubic. Okay, 20,000 cubic capacity is what you will normally find. They can again carry your LPGs, your VCMs, but here another use of them that they normally carry is ethylene. Okay, now ethylene, when we are talking about, it goes to minus 104. We will understand that. So since this is semi pressurized, the pressure range is 5 to 7 bar. So in the fully pressurized, what we saw, 17.5 bar, right? Here it is 5 to 7 bar, and it can go to, typically if it is say LPG and all, minus 48 degrees. Okay, or minus 50 degrees. So then basically they are capable to handle your LPG cargoes also in the fully refrigerated. I will touch, don't get confused. Okay, so just understand now, the in the semi pressurized, the pressure rating has come down. Same types of tanks are used, type C independent tanks, but with a lesser pressure rating. Okay, and the temperature that it can handle are much lower also. Then we will see fully refrigerated gas carriers. So the one which you can see over here is what you have normally, like, read and understood as VLGC, very large gas carriers. Okay, so here it is like fully refrigeration process which has been used to keep it in liquid form, right? So deck is pretty much flat over here. VLGC, when we talk about, they are close to about 80 to 85,000 cubic, but recent orders, and there will be like a few ships which will be delivered in the 93,000 to 1 lakh thousand range also. So then people might start categorizing them as ultra large gas carriers. Okay, so far this particular word is not in the market, but as the ship goes, again driven by economic of scale, right? And you will find some mid-size gas carriers also, basically for fully refrigerated. They are close to about 40,000 to 45,000, but here also that figure is going towards 60,000. Okay, so 60,000 are also being designed, and orders are being placed. So you will find in that 40 to 60,000 range, you will be able to call them as mid-side gas carriers, and these are VLGCs, what you can see. Another form of this, so okay, the pressure. Okay, so there we saw 17.5 bar, we came to 5 to 7 bar. Here it is 0.7 bar. That is the max pressure that the tanks will be designed for, okay, with safety valves set point at those pressures for the fully refrigerated ones. Now these are basically designed to carry more cargo at a longer distance, okay, transatlantic and all. Sometimes these are also used as parcel tankers also, depends, okay, doesn't limit it for only like longer passages. The other type of fully refrigerated tankers which you see is LNG carriers. Okay. So now normally like company calls, you will see some advertisements, they will talk LPG ships, LNG ships. Okay. So these are ethylene ships. These are basically commercial terms that we are using it to identify, and most of the times it could be correct because they could be designed to carry only those specific types of cargoes. Okay, but technically, as per IMO, the distinction is fully refrigerated, semi pressure, and fully pressurized tanks. Okay, under that, then you will have all these subcategories. So I hope this particular confusion basically is cleared of yours, right? So then we will just try to understand about the gases. Okay, so this is how the LNG carrier looks like. Membrane tanks and all I will come, okay, I will touch upon those. So let us understand about this basically gases. Okay, this is something which is very important. On the left hand side you can see the cargoes, and besides it you have the boiling point. So only when you lower the temperature, so if you are using refrigeration, okay, as a means to liquefy a gas, so you have to get it to the boiling point, only then you will find that those gases basically will change their state into a liquid form. So when we talk about LNG, we go to minus 161 degrees. When we talk about ethylene, we go to minus 104 degrees. Ethane comes to 89. Okay, propane minus 43, ammonia minus 33, butane when we talk about minus 5 also. Okay, depend minus 0.5. Okay, there are three variations of butane, okay, over there. And then when we see into the vapor pressure, that is the pressure that you have to raise in order for you to basically convert it and liquefy the gas. Okay, so here then you can decide how to do, what to do. Now we will take a fully pressurized gas carrier, and if you have to say take propane, so you require what, 15.5 bar, okay, atmospheric, and we have designed the tank at 17.5, so you have a 2 bar margin over there, so you can basically carry it in that particular tank. Now ammonia 17.8 bar, so if you want to carry in a fully pressurized vessel ammonia, so you will have to have a pressure set point of close to about 20 bar. Okay, then only you will be able to carry it on a fully pressurized carrier. The same thing if you want to use the same tank to carry say butane, which where pressure is about 4.3 bar, you can easily do so. Okay, so this basically boiling point and vapor pressure basically helps you design and where and how much quantity you want to carry, the characteristic of that particular gas. This is what is the driving force to decide in which type of gas carrier that you want to carry that cargo. Okay, and then to provide flexibility and all, then some additional aspects will also come, which we will touch on in a subsequent slides. So next we will try to identify the hazards of these cargoes, right? So we have seen the boiling points going into the negative temperature, it's basically cold, like low temperatures. So one thing is when we say personal hazard, we can talk about frostbite, okay, cold burns, if it is basically comes in contact with us. Similarly, if this cold cargo, if it spills on the deck, then you will have issues with the metal, okay, cracking. How? Brittle fracture. Okay, this is something similar what you can relate with Titanic, right? So while preparing the plates and all, they had added few elements which in this Atlantic conditions, in the cold thing, it lost its ductility. It became brittle. When it came in contact with the iceberg, it basically ruptured. So something similar can occur. Now this cold temperature metals is basically is expensive than the usual steel which we use to make the hull of a ship. Okay, so the cost will increase. So there are ways to basically reduce the use of such low thing, and which I will touch you in another slide. Okay, so we will understand. So we have this hydrocarbons which we use, correct? So hydrocarbons, basically flammability is a issue. Then you have chemical also gases, so that can introduce your toxicity, that is poisoning. Then you have other gases like nitrogen and all, which are there, basically displaces your oxygen and all. So suffocation, okay, asphyxia, right? Those will come if the chemicals are there. If comes in contact with your skin and all, chemical burns, those will come. There was another thing which this is basically for personal hazards, right? But then this cargoes also, they can react with say water, okay, to form hydrides. Well, let us understand. We go back again to the previous slide, right? So here we have seen negative temperatures. So water freezes at 0, correct? So in this temperature, if there is a water, it will form ice. But however, here the technical word what we use is hydrates. Okay, hydrates. We don't call it as ice. So if you find water over there, becomes hydrates. How water comes? It could be while putting inert gas in the tank. Okay, we remove the air by inerting, and then we will basically take the gas over there. So if there is water in the inert gas, that is your source. Then we talked about no liquefying, okay, refrigeration. So in a typical refrigeration plant, in the condenser you find water, right? So something similar plants what are being used on board also. So if there is a leak in your condenser, you find water in your tanks, or you load the cargo with contaminants itself. Okay, so these are some of the ways where you will find water itself. Sometimes this cargo also reacts with itself, like aging. Okay, there is a lot of talks about your VLSFOs and all, no shelf life, consume it within 12 months because it age and it segregates, decomposes, changes its state. So something similar thing you can observe with few of the cargoes also. Okay, so they have a very short shelf life, and then they are also transported with inhibitors also, depends on cargo. Then few of it also reacts with the air. Okay, if there is air, then it will react and it will start changing its form. And also with other cargoes, for example, like we spoke about this VLGC, right? They are designed to carry LPG, that is propane butane. They can also carry ammonia if it is designed so, but then they are not compatible. Okay, so you have to basically do inerting with one cargo and then introduce the other cargo, right? So those are the things. And then what you will find is this cargo also reacting with the material, the cargo tank material, the automation, the piping material. For example, ammonia, it introduces something known as creep corrosion, okay, stress corrosion. Now if it is like magnesium and all, so you have to use or stainless steel material, then only you can
Then
basically
you can
use.
basically use.
Okay,
Okay.
then
Then
another thing,
another thing,
rollover.
rollover.
In the rollover, what it is basically occurs in your LNG ships. This is more pronounced in LNG ships. So there is a stratification. So if you take a tank, say 50% of the tank, okay, you divide the tank into 50%. So the top half will have LNG as a cargo, but the density is much higher. Okay, and the bottom part, the density is lower. Okay, so this basically occurs like when it is on a long voyage. Okay, it doesn't happen in an instant. So over a 2 3 weeks period, then you can find that stratification is occurring, wherein a higher density is accumulated on the top, lower density at the bottom. Now natural tendency, what, higher density has to be lower, the lighter particles basically are on the top. That is the natural tendency. So obviously as the weight increases, it reverses, changes over, and this is an instantaneous process, and it results in your stability issues. Now try to relate it with your naval architecture. So as density increases, the weight will also increase, right? And now within a minute or so, you just imagine that it is just changing over. So there is change of weight, so your meta center and all those things will change, so it basically affects your stability of the vessel. So that is what rollover is all about. So these are few of the cargo hazards. Now we have seen design of the ship, condition of carriage, and characteristic of all these cargoes and the associated hazards. So so in order to have a control in all of this, uh, IMO basically came up with a code. Okay, IGC code, that is a short form. A full form it stands for is International Code of Construction and Equipment of Ships Carrying Liquid Gases in Bulk. Okay, so it is a mandatory requirement under SOLAS Chapter 7. Okay, and it has been since 1986. The latest version is basically 2016. Okay, that is the latest 2016 IGC code is or how it is called. Now what does it govern? It basically looks into your design, it looks after the construction and the equipment which have been fitted. Okay, in the lens of what, minimizing risk to the ship itself, to the crew, and to the environment. These are the major focus. Okay, now here I will like to tell you something. Okay, you must be have read in the news now, LNG is coming in a major way for use as a fuel for propulsion of the ship, right, for generating electricity on board. So similarly you will find that LPG also being allowed, hydrogen is also is coming, right? So originally if you see, LNG was the only gas which was allowed for propulsion purposes on a ship. LPG is also not allowed. LPG and all basically came under IGF code. This is another code basically that IMO has come under alternate design approach. So this alternate design approach has been now or a interim solution kind of a thing. They have basically allowed to use these fuels. Similarly, hydrogen also is allowed as an interim measure. There are no provisions in this mandatory code that you will find. Okay, now these are all on trial basis. They will see for a few years how it works, which design, whatever challenges and all, and then there will be revisions which are coming. There is a plan from IMO that in 2028 there will be a major revision under IGC code, wherein all this hydrogen and all requirements for those basically will come into the picture. Now in this interim measure, for example for hydrogen, okay, so it is only designed for hydrogen, you cannot use it for some other things. Okay, so there are some limitations and all which have been placed by IMO. Okay, so in by 2028 they will come up with firm regulations. Now whatever approval is basically ship specific, project specific, given by the administrations, and there are provisions for such approvals within the code. So this is something in advance, like, because a lot of things which are basically coming, you will read in the news, so you should be able to make sense of it. Okay, so since as this IGC code is basically specifying how the ship is designed and constructed, we'll see like which are the special features. Okay, we'll look into the special features which makes a gas carrier apart from the the cargo that it carries, okay, the physical aspects of it. We will try to understand all those. So one thing what you will find on a gas carrier, especially your I would say semi pressurized and fully refrigerated, is something known as airlock. Now, as we have said, these two ships basically will have a refrigeration system to cool down. Okay, they will have a refrigeration system to cool down. So for that, like, you can relate to your normal refrigeration system on board, right? Could be for provision system or for the AC. You have a compressor which is basically driven by by a electrical motor. That is your drive, right? Prime mover. So similarly, you will have a compressor driven by a electrical motor. We keep both this equipment in a separate compartments, okay, and the drive, basically the shaft, basically passes to a bulkhead which is common to both the compartments, okay, and there is a gas seal and all which basically is provided onto it, okay. So the electrical motor room is known as motor room, and the compartment which the compressor is located is known as a compressor room or cargo compressor room. So what happens is, you have a ventilation system fitted in your compressor room. So it is like in a partial vacuum state. You keep in a pressurized state the motor room. So you blow in more air. You take the air outside the normal cargo designated area. That zone 1, zone 0, zone 1, zone 2. You might have learned about in oil tankers and all. Okay, so it is taking outside the zone 2. Okay, putting, so it is kept under pressure. Now if you want to do for near your watch keeping and all, you have to enter the motor room. If you open, then you will lose the pressure. So there's a reason why there is another compartment which is made, and there are two doors. So you open the first door, from the deck you enter. Okay, so you are in the airlock. This space is now the airlock. Then you open the other door and you enter the motor room. This airlock is also kept under pressure. Now, additional features about this airlock is, there are two doors. So if someone is in the motor room, he wants to come out, and at the same time someone is wants to enter, and they don't know how to know. So if any door is open, there will be an indication, visual indication. Okay, a light which basically start rotating. Something what you see in the ambulance and all, no, rotating rice and all. So similarly, indication will be there. If both doors are open together, this indication, visual indication will be working, but additionally will be a audio or alarm sort of a thing, which will basically sound to ask them to close the doors. Someone, both doors are open, or they have not closed and you're opening the other one. Okay, so these are something specifically to gas carriers, this airlock. What you find is, another thing what you find is your ESDs. Okay, this basically can be operated remotely from cargo control room, bridge, your fire station. Okay, remote operation to the terminal is also there. So if the ship is in the terminal, this terminal can also operate the ship's ESD. Okay, that control is also given. And you have manual points also. So someone who is there, like fire, manual call points you find like in each alleyways and all, you can utilize those also. And if there is a fire, localized fire, you have something known as fusible plugs. So those can also activate your ESD. Purpose is basically to stop the pumps, to stop the compressors, to stop the flow, and secondly close all the valves which have been opened from the tank on the manifolds, so there is no further leakages from those, to basically isolate. So on deck, what you find is water spray systems. Okay, and you have DCP, like on oil tankers and all, you will find foam system. Here you have dry chemical powder system. Here you will have portable hoses, and you will have fixed monitors at the manifold, which could be remotely operated or locally operated. So operation can be any place. Water spray is something unique, wherein fixed nozzles and all are there. A fixed high capacity seawater pump is there. Okay, it is different from the fire pump, and you can basically creates a rain. Now I had told you, earlier, that low temperature plates which we are using. Now you can imagine, the whole deck, anywhere the spillage can occur, right? So you will have to utilize this low temperature things to avoid the hull getting cracked and ship breaking into two parts or more, right? So this water spray basically helps you in that. Okay, this is the first feature. So what happens if you start this pump and the spray occurs, there is a natural cushion or a blanket of water which basically happens on the deck. So any cargo which is leaking basically comes in contact with this seawater, and this is moving to the scuppers, and also it basically takes away. Okay, it doesn't allow it to accumulate the natural chamber of the deck and all. Okay, so it basically takes away from it. So low temperature plating is basically limited in way of your cargo tank domes and your manifold area. Okay, so this is one place. In order to minimize leak also, these pipes and all, okay, we don't have flanges, those are welded throughout with provisions for expansion, which you will normally find on oil tankers and chemical tankers also. Okay, but these are welded throughout. Even valves are also welded. Okay, and so this basically minimizes the leak on the deck. So these are some of the design features basically elevates the requirement of low temperature skill to for throughout the hull, and it basically keeps the cost down. Now in the tanks, when we will see the construction, but here I will touch upon that. uh, Imagine a bulk carrier. A bulk carrier, basically you will find that hold is there, and that hold you will find is tanks basically placed into it. Okay, and they are basically covered. So this space between the tank and the side shell, which basically forms your ballast tank, okay, that is known as the hold space. And these are also protected with relief valves. Okay, PV valves are also fitted in the hold space. You don't find PV valves like in an oil tank or on the cargo tank. You only have relief valves on the cargo tank. Another feature is vent mast. So if pressure rises and all, you want the gas not to accumulate near the tanks. You want it higher up. So you have all these towers wherein the gases are laid to. Similarly, if there is any leakages also, it is led to vent mast. Now you will find this dual fuel used on normal oil tankers and containers, bulkies and all. So if there also they are using, you will find a mast, dedicated mast. So if there is like a gas changeover, there is a trip, gas trip or something, the gas which is there is basically a purge function is there, and everything is led to your vent mast. So that is important. So a lot of vent mass basically comes into the picture. Now when we were talking about different types of ships, we always saw that it was on cargo tanks were in positive pressure, right? 17.5 bar. We were talking about 5 to 7 bar, zero point 0.7 bar. These are like above your atmospheric pressures. The main thing is that we have seen in the characteristic of the cargo that it can react with the air. Sometimes the flammability also is there. Okay, so you don't want that air to come inside your tank, so they are always kept into a positive pressure, so the cargo can come out, but air will not go in your tanks, cargo tanks. And in order to basically pressure control basically is done by a liquefaction plant also while discharging, also that can also result into pressure going down. So we have pressure switches and all basically with a set point which basically trip. You can relate it to say your refrigeration system. Okay, low pressure. Okay, it will stop, basically stop. The moment pressure rises, then the compressor starts. Like it will just stop and it will give you an indication. Okay. DCP is already. Then we have something known as gas detectors also. These are fixed ones in engine room, in the accommodation at various places, okay, and in the cargo spaces, in the motor room, in the airlock, in the compressor room, in the holds, and it is basically monitoring in a 30-minute cycle continuously all the spaces, okay, cargo spaces specifically, and it will give you an indication. Second, the last point what I want to highlight is the loading part. When you're loading, say in a oil tanker and all vapors and all, no PV valve is open and you're releasing all those. But now to that also that VECS and all those things have also come. In gas carriers, you never let the vapors basically go to atmosphere. Okay, so you either contain those inside, which you normally will find on LPG ships. The vapors are received. Whatever extra vapors which are generated basically will result in rise in pressure. So you're removing this, you are again cooling it down and returning back to the tank. Now this is something which is not practical in LNG ships. So you basically return the vapors to the terminal again. Okay, if you have to basically again reliquefy this, then the loading rates will come much lower and the loading times will increase into 2 days, 3 days. Okay, so it is not practical, economical sort of. So you are basically whatever vapor is generated, you basically shift it to the terminal. So then they will basically they have the higher capacity plants and all for them to reliquefy, or they will flare it depending on their requirements. So that is how uh, this thing is all governed. Okay, now having known this, we will just try to see some of these features on a gas ship. Okay, so here moving on to a pressurized ship, you will see your cargo tanks. Okay, these are just like your air bottle tanks basically placed in your cargo hold. Part of it is protruding, it is just directly painted, there is no insulation involved here. This is your actual metal. Okay, only for corrosion and all you are doing the normal painting and paint schemes which are there. Here you will find basically your mast which you can see. Okay, one mast for each tank, dedicated ones. The relief valves basically will be connected to those, so anything venting basically is on top, so there is no accumulation in way of the tanks. Second thing over here in the aft section, you will see the electrical motor with a straight drive to a centrifugal pump. It's a cryogenic pump which is basically used to pump. Okay, this is a straightforward system. Things get complicated in a semi-pressurized system. So here you will find one specifically a room on the deck which is known as a compressor cum electrical motor room. Okay, where the refrigeration system, actual word is reliquefaction system or plant. Okay, that is the word which is being used. It's basically a refrigeration system where compressor and the electrical motor which basically is there is used. So all the vapors goes over here, there are condensers also inside which basically will liquefy, and then lines going back to the tank. Additionally, because these are like mostly designed to carry multiple cargoes and all, and to do grade change, you basically have a deck tank. In that tank, basically that other cargo will is already there. Now, normally propane, butane you can interchange, is not much of a problem. The moment like it is liquid free, only in gas form, then you can put the other one. Okay, and that little bit of contamination is acceptable. There is no issues with the marketability of the product. But if say you're using ammonia and all, then mixing is not allowed. So so in order to save time and in the voyage itself to do the grade change, you normally have a deck tank with the other cargo which you basically use, and it is sufficient only for cooling. Okay, do replace the whole volume into gas plus ready it for that particular temperature to receive at zero. Okay, so these are things, and you there is a mast and all as usual. Moving on to the fully pressurized one. Okay, so again, compressor room come motor room is there. These are larger ships. This is about at least four tanks, so more number of this vent mass over here. Okay, now these are all independent tanks. When we talk about LNG carriers, you see there is a projection. Most of the LNG carriers have projection. Okay, there is one type of tank where it looks similar to a LPG ship, but then it is designed to carry LNG, and we will see into that once we check the plants. Okay, so here you will see that these are like prismatic things, but then here what is happened, these are not independent tanks. Okay, so you have the ship's hull, and then on that you are putting a lining of insulation and some cryogenic material. We'll go into a little bit more details in the subsequent slides. So here again you will find the masts over here. Okay, right in the corner next to the accommodation on the side you will find your liquefaction compartment, motor room, as well as your compressor room. Okay, so here and then one box, one compartment on the between the manifold and the motor room and compressor room, that is a DCP station. So here you will have that DCP cylinders along with the valves and all for monitors and hoses is where you will find all those. Okay, so we will just try to understand another concept of the tanks. We will understand the tanks. Now IGC code basically have categorized into four main types. One are like integral tank, membrane tanks, semi-membrane tanks, and independent tanks. We'll just have a look what those are. Okay, so this basically what IGC code talks about. Integral tank is basically your hull of the ship directly forming, containing the gas, and it is normally not allowed. Okay, so integral tank, they don't allow you to carry this sort of cargoes. Then other one, like in LNG ships and all we have seen, is membrane tanks. Okay, the design part when we will come to know, but here the requirement is they want a complete secondary barrier. So if the whole one tank is there, so they want another concentric lining along the tank, so it's a tank within a tank, you can understand. Then you have something known as semi membrane tanks, which basically again, complete secondary barrier they want. And the third one, fourth one, which is important and predominantly used in on gas carriers, are independent tanks. So there's an individual tank basically placed in the hold of a ship. Okay, and they are subdivided into Type A, Type B, and Type C. In Type A, basically a complete barrier is required. Type B is partial secondary barrier, and Type C there is no secondary barrier which is required. We'll look into it, why it is what it is. Okay, don't get confused into all those. Okay, so here another thing is below 10 degrees down to minus 55 and below minus 55, you see the over here. Okay, so predominantly this is what it is. You will find membrane tanks which have taken utilization, and independent tanks which are predominantly, other types are not generally used or favored, like the tilt is towards that. So we will understand now what is this independent tank. So you see this is the outer hull of the ship. Then you have a hooper tanks, water to carry water ballast, and you have a double bottom for water ballast. So in between you have that space, the hold space, right? In that you have a tank which is placed. Now this design is a prismatic. Okay, it looks like a prism, correct? So we have seen now a prismatic Type A tank basically will require a secondary barrier, complete secondary barrier. So that is basically what you can see in the inside the tank. You find a little bit of insulation, and then you have another basically tank lining which basically comes into the picture. So tank within a tank. These are basically supported like foundation of a main engine or pumps and all, you will see, but not that it is not bolted like those engines or pumps that you normally see. You will find that there is a wooden piece, a special type of wood basically, and it is just rested on that. Okay, so if there is a water and all, if there is a rupture in the hull, say side shell, and then water and all will come, depending on the how much water, and if it is filled which cargo, because each cargo has their own density and all, these tanks can float and displace. Okay, so they are basically within a tank, just placed. It is not secured. So that is what the main thing is. Insulation basically, because you can relate it to your provision chambers, you know, you have this meat room, fish room, so they are also insulated, and inside you carry all this provision. So similarly, why? Because that heat loss, ingress, right, and you can maintain it into that those temperatures. So same concept applies over here also. Then we'll look into type B tanks. So on the right hand side, what you see over here is basically a Moss type, spherical ones, predominantly used for LNG. Okay, these are basically was seen earlier, predominantly made in Japan. Japanese shipyards were the ones who have were building this. Okay, they basically made that invention, and they were favoring it. But however, now you will find that no longer you will find such ships, because there is a lot of space which goes. Now what is GTT tanks, which you will look into. Another design that they came is SPB. Okay, on the left hand side, which you can see over here. So this basically a tank is constructed similarly to your LPG tank, but they can hold LNGs. Okay, and so main distinguishing factor over here is there's a robust tanks. They will not fracture so easily and all. And there's a reason why type B tanks partial secondary barrier is what they have allowed. Okay, so what you have is basically a small tray beneath, which is of low temperature material, right? And if there is any leak, basically it is contained. Now all the secondary barriers, when we are talking about IGC talks about, tells that they have to design such that it has to hold that cargo for minimum of 15 days. Okay, in this 15 days, the moment you discover, then you have to go to a port and all, and then you have to discharge the cargo. Okay, so it gives you that 15 days of uh, grace period to unload it. Now this SPBM, what I talked about, if that particular tank are installed, it has a flat deck, same to what you will find as a LPG ship. Okay, these ships were, again, the cost factor of those are like higher, so they are not being utilized as a project. Like only two ships or something were built and they were running, so most likely they are close to, they are likely either scrapped or at the stage of scrapping. Okay, these are quite old ships. This particular tank technology is not predominantly favored. So here you can see on the right hand side, no, this whole aluminum based, okay, with a nickel alloy being fabricated, and then they are basically lowered. Okay, so this is how they look into. Okay, so these are type C tanks, independent type C tanks. So I talked about the semi pressurized bilobe, and also this is how those are. Okay, this is on the left hand side bilobe thing. We basically utilizes more, okay, space, horizontal cylinders. So these are some of the systems that you will find in a fully refrigerated system. We'll see another picture wherein they are installing. You see, the outer hull is prepared, the hold is there, and these tanks basically are just lowered, and then they are going to cover it out. So these are individual tanks lowered. We'll look into membrane tanks. These are basically what you will find on ethane carriers, your LNG carriers. Okay, so the outer hull which is there, you have this is as a ballast tanks. So against that you will have the first plywood or something which is put okay, in which basically you will have insulation. Okay, then you will have the first metal sheet basically which comes, and it is known as secondary membrane. On top of it you will find another insulation basically covers. Okay, membrane we have seen, complete secondary barrier as per IGC. So you have the secondary barrier is complete throughout. Okay, and then you have the primary barrier, in which primary barrier basically the sheet which is there, which will be in contact with the cargo. Now in between you'll have towers in the tank, wherein the pumps, main cargo pumps, stripping pumps, fuel pumps, depending on type of system what is there, which will be mounted. And here you will have another small opening which is only opened for the gases, where the vapors are basically removed, and it is known as a vapor dome. So you have a liquid dome and you have a vapor dome. Okay, a fixed emergency pump can be accommodated, or there will be a provision and you will have a spare emergency cargo pump which you have to open and lower. There is a flap type of valve and all located. So the moment you lower, you close the top, and then you keep on lowering. The moment it touches, the flap will open and then it will have access to the liquid, and then you can utilize those pumps. So there is no escape of gases and all. You utilize nitrogen, so there is a specific procedures to that. Okay, so what happens over here is, in the membrane thing is, the thin the sheets which are used could be of zero point 0.7 to 1.5 mm thickness. Okay, it could be SS or could be Invar. Invar is normally thinner, zero point 0.7. If you're using stainless steel, it basically looks towards 1.5 mm thickness thing. So we'll just look into a tank, actual. So again, it is a prismatic design. Okay, with the tower which you can see supporting, and the pumps over here. This is not touching over here. There is a clearance and it is a floating one. Whatever weight of the pumps and everything is basically is on the top. That is a main highlight over here. The design for this prismatic things, see, we have seen that these are like sheet metals, and it is basically clinging on to your insulations, and then the plywood and all, which we will see in the subsequent pictures. So what you will find is, if liquid is over here, there is a lot of sloshing. There is no another division within the tank, and then this can get destroyed. Okay, so that's the reason why there is a limitation that how much you cannot load half of this tank and sail. They don't allow. Only LNG ships basically for use for bunkering, and they are within the port limits, then they are allowed. But if it is sailing, they are not allowed. So you have to have the liquid somewhere around here. So obviously you can see the surface area and the volume is quite less. So if the movement which is there and the sloshing load will be much less, or it will be closer to here. Okay, so that is another design feature which you will usually see. So here you can see example over here, wherein this sheet metal is there. Okay, they are basically bent. One is to give the strength. Okay, complete sheet metal basically, if it is plain, it will not resist forces. And second thing is expansion and contraction because of this cryogenic temperatures. So this band basically is going to take, and then you will find all this insulation, how they are basically held in place. I have few more pictures to show you. Okay, you have like Mark 3 NO96. So the main difference over here is the material. So in NO6 you will find Invar being used, and the thickness, as I told, is 0.7 mm. And you try to install Mark 3 systems and all. So you normally use stainless steel of 304 grade, right? And thickness is about 1.5 mm. Then type of insulation, the thickness of insulation also varies. Okay, that's what makes the things different over here. These are the some which basically, and main highlight is what to reduce the boil off. Boil off means how much vapor generation is controlled to the total capacity of the tank. Okay, so here we can see the sheet metal, how it is done, how it is like in the block, no, it is cut, prefabricated, and it's just assembled in the tanks. So these are all about membrane tanks. We'll just have a look inside of a type B, MOS system. Okay, the spherical ones. So again, tower, and this is how it is. And in the bottom, you see for inspection, this is the cargo hold. So you can come over here down to have a access. Here there will be a nice tray also. If leakage is over here because of the shape, small drops, they will basically come over here. Okay, and will get accumulated over here. So there we have gas detection system, you have a uh, float valves and things like that. Those are additional features. So these are like different types of tanks that you will find on gas carriers. uh, then we will just touch upon uh, how this pressure is controlled. Okay, so one what we have mentioned is reliquefaction cargo vapors. Okay, so you have a refrigeration system basically which is there, uh, s- equivalent to the one which you have on ships for accommodation or provision. Okay, take the vapors, you compress it into few stages, two stages or a three-stage compressor. You send it to a condenser, liquefy it, and that liquid is basically sent back to the tank. uh, Now what happens is this becomes very uneconomical with when we come to methane. Okay, so you might utilize something known as thermal oxidation, wherein in simple terms it basically burns the cargo. Okay, whatever vapors are generated, you are just burning it. Okay, so it's a huge tower with a pilot igniter or a spark plug and blowers. Okay, you're dumping in a lot of air, you're opening these vapors into it, and you're just burning it off. Okay, also known as GCU, gas combustion units. Okay, so these are also used to control your tank pressures. Another thing is pressure accumulation. What you will find is some designs are will have dual pressure rating. Okay, sometimes you will find sea mode, harbor mode. Okay, sea mode is normally the lower pressure. In harbor, when you are there, we are loading and all, where the pressures will go higher, and to buy more time to use your reliquefaction plants and bring it under control. So you can choose to go change the set point of the relief valves to a higher value. Okay, in LNG ships, also new ships which I have worked on, so they have come with it. Initially, it was like you were maintaining at about 360 millibar pressures and all, and then your relief valves was set close to about that. Okay, now the newer type of ships, it goes to about 700 millibar. Okay, it's more than double. And normal range when we were carrying it to about 280 millibar and all at sea, it varies, it's not static, it's about to say 220 millibar to 280. We could touch to even 300 sometimes, depending on like summer months and seawater temperature going high and all those stuff. uh, these are closer to 400 50 bar and things like that. Okay, any primary. So the but in design, the quality of tank work also have improved to hold those pressures. And then you have something known as liquid cargo cooling, wherein this liquid okay, the liquid is basically taken from the tank and is passed to a heat exchanger, and you use helium and all refrigeration plants basically cool it again to say minus 167, and then you uh, resend it. So here you are not cooling the vapor in the liquid cargo cooling. You take the liquid which is close to say 160.5 or 159.2 degrees and all, that is the temperature of the liquid. Okay, it is in liquid form itself. You take those from the cargo tank and you cool it to minus 167 and you return back. Okay, so that is also being employed to control. Going forward, in the reliquefaction plant or refrigeration systems, you have direct systems, you have indirect systems, you have a combination systems also. Okay, so there are multiple types. On LPG ships, you usually will find direct systems. On ethylene carriers, you will find indirect systems. Okay, so you have another refrigerant basically going into a heat exchanger, and you're taking the vapors of ethylene and you're cooling it and you're redirecting it. So these are some means of cargo vapors that you are handling. So care of cargo during voyage, also during loading times also. So moving on to the last topic. Okay, I've exceeded the time and thank you for being patient. So we will just try to understand some of these cargoes the gas carriers are using. They are found their purpose as a fuel. Okay, so we'll start with LNG because that was the first thing which basically came into the picture. So I also mentioned that they are like transient in nature because thing is, compared to this liquid fuels of VLSFO what we are using and LSMGO and all, the carbon percentage is less. Okay, that is the reason why this have been chosen. Secondly, then the amount of there is usually there is no sulfur present in this LNG as well as LPG. Okay, so is close to nil SOx production. Why it is not zero is because you are using pilot fuels to ignite these fuels. Okay, and these pilot fuels are again you are using LSMGO, so that does produce little bit of your SOx in that. Okay, so that's the reason why they are not less. So here it's about 25% less carbon dioxide that it is being formed compared to 80% less NOx which is being generated. Okay. One important thing over here is direct gas injection. Usually you use gas vapors and then you inject. But in LNG, when you say Maggie engines and all, no, so they use those, and it could be diesel cycle. Then you have this 50 DF engines, Vatsila ones. They use auto cycle, basically. There, basically, it is mixing. Okay, you take the vapor, and then in way of the during the uh, suction stage, you since the charged air, okay, from your turbocharger getting cooled in your cooler, air cooler, once it comes inside the combustion chamber, that is the time when you're injecting this vapor. Okay, LNG in a vapor form, it gets mixed and then you're igniting it and burning it. So those are the types of engines that you basically will find. Okay, moving on to LPG, you will find that it is again pilot injection and all is required. So it basically produces 95% no less emissions. Okay, NOx also is quite less. You can use auto cycle also in this. But here main difference with LNG is you are basically in a liquid form. You are injecting LPG in your combustion chamber. It is not in vapor. So the moment you are injecting that mist formation, it basically vaporizes. Okay. So that is known as liquid injection in those engines which are basically specifically designed to basically consume your LPG on those ships. Then another thing is about your ammonia. Okay. Now LPG. I'll just talk about LPG. They are basically used on gas carriers who are carrying that as a cargo. So similarly, ammonia presently few ships being designed and all, they will be carrying ammonia as a primary cargo. However, these engines which have been designed, they can basically cater to ammonia or LPG, because that flexibility is be provided, because gas carrier, they can be utilized to carry either of the cargos. So when you have that cargo, basically you're basically utilizing it for propulsion. So ammonia is also come into a big picture because there is no carbon involved into it. Okay, so that is the main thing which is come into it. But then production and all, it does have issues, to produce it. No, when we are looking at well to wake and all, so then they are diversifying it into your brown and green and all those color coding. However, this ignition quality is not very good for ammonia. Okay, so it when it is like ignited, it basically, there is an explosion kind of a thing. So they are basically trying to control those, so that you have, I would say, more running hours of your combustion chamber spares. And another disadvantage with ammonia is lot of NOx which it will be produced. Okay, since see, here n is there, so nitrogen. So compared to your LNG and LPGs, the NOx production is relatively on a higher scale. So you will have to have a SCR. And in LNG, basically an auto principle, tier 3 requirements and all, with regas and all those thing, you could meet those requirements, tier 3 requirements set out in Annex 6. But here you cannot do away with the SCR. So SCR will be a necessary equipment associated with your ammonia when it is used as a fuel. Okay. Also, its density and all is quite less, and here about 80 to 80 bar is what is required, to be injected. Basically, liquid injection, but 80 bar is what is the requirement for ammonia, which is basically there. Uh, some advantages what they are talking about is because ammonia can be a carrier for hydrogen. Yeah, hydrogen is something which is also developing, and going forward, you will find that hydrogen and nitrogen will be predominant fuels, basically, uh, which we'll be using. So now, recently, in the just I would say this week itself, beginning of the week, when this gas tech forum, so there was a first ship with nuclear propulsion which has been signed in Korea. Okay, looking into hydrogen. Okay, now this is something unique challenge which comes because boiling pressure is 259, right? And then temperatures. So they are talking about ammonia, which will be a carrier. So ammonia is minus 33 degrees only. So you don't require such cryogenic states. And then to reliquefy it to negative 259.9 degrees, you can just imagine the amount of energy that will be required. So these are few challenges that they are basically facing. This is basically in a development phase. Okay, and there is another thing is, uh, what is it? Energy dense, and its flammability also. Flammability, I will just maybe in the movies and all, olden movies, you could have seen these airships and all, no, during World War, huge balloon which is basically carrying. So they were using ammonia. Those balloons were filled with that, so that lift and all, no, and you could use. And then you had this fans to guide basically and navigate. But they were prone to fires. They were prone to fires because it is very flammable hydrogen. So that is another safety aspects that basically comes into the picture. Right, so these are the few gases basically which are being considered, and we will find more developments coming with all these projects, right? So with this, I conclude my presentation, and it's time for queries. So whatever questions that you have, topic is vast and I have taken 1 hour and 40 minutes of your time. So let's be specific to the no whatever being discussed. It's all to you all guys. Any queries that you have, you can ask. Come on, questions. It only means that either you have not understood anything or you have understood everything. I don't think I'm so good that I explained to you so well that you have understood everything.
Yeah, hello, sir.
Desmond, can you just for this LNG as a fuel, the slip, methane slip which we have, there are, I think, after the combustion, any retrofit or fitments are there for this treating of the methane slip?
Yes, this is one of the disadvantages with LNG. One thing is, we'll try to understand what is methane slip. So once the combustion takes place with LNG in the combustion chamber, a 100% combustion doesn't take place. So there is like point 0.1%, 0.2% or something. What they are talking about, that LNG basically escapes with the exhaust gases and it finds itself in the atmosphere. Okay, the issue with the small quantity is CO2 is our benchmark. Okay, wherein we are basically uh, looking into the greenhouse gas effect at global warming potential of a gas. So methane has a higher global warming potential. So little bit of gas, the effect that it does is much larger. So it is a concern. So there are a lot of designs which have changed by means of electronics to control the combustion. So you have a much thorough combustion of the gases. Okay, so they are trying to reduce that. Second thing what they have done, approach this to address this issue is changing your combustion geometry. So you don't have like some pockets or something, where this gases remain and then they just leave along with the exhaust gases. So the flame basically reaches throughout the chambers and it comes in contact with, there is no like gas rich chambers within the combustion chamber that it will not ignite and then it passes through. So these are the things. Another addition in this, what they have done is this gas exhaust gas recirculation. So part of it is coming and then you're recirculating, so that has also helped to reduce. Okay, so there is a reduction of 50% to say 10 15 years back when this first LNG no engines, dual fuel engines basically came into the picture. So from there to present, 50% reduction has been achieved by all these measures what they have. And there are research which is going on to reduce it further, but presently what they are talking about is 100% reduction won't be. And another point that you have to see that risk reward ratio, this being a transient thing, another 2 decades down the line you will find other fuels taking over. So it will be limited now, we have to, as far as technology is reaching. And what I have read from makers, they are basically signaling it to that we have plateaued to what we can advances we can do. Maybe another 10% increase and it goes to about say 60% from first generation of engines, that what we are going to achieve. Okay, I hope this basically addresses your uh, query with that. Okay, Mr. Datta has asked in the chat, then how does it become economical if they burn it? Can you just be specific with respect to what you're talking about?
Yes, sir.
Maybe you can
Means you were
unmute
talking
and
about the gas combustion unit, where you were saying that in some types they burn the the gaseous substance which is getting generated.
you're not very clear. No, your voice is getting broken. Maybe because of the internet connection you might be on board. Can you just type it? So because unable to understand. Okay, another thing is by Mr. Faria, ammonia is also toxic. Yes, those are the challenges that are faced. Correct. Then we have with respect to DFD engines, please explain liquefied gas transfer arrangements to of gas tip of injector as gas considering oil cam tankers. See, dual fuel diesel electric drives, so it's basically generators. Okay, Vatsila 50 DF engines, those are the typical engines that they are. Okay, V type or inline engines. So here what they basically work on auto principle, auto cycle. So here you have this, gas valves which are basically placed within the charged air connection to a in way of the gas cylinder. Okay. uh, these gas valves, if you look, they are similar to your air compressors, plate type sort of valves. But in air compressors, you will find that they are operating in differential pressures, right? For opening, closing. These are basically a magnetic type of valve, a magnet, which are energized from the by the electronics basically. So what you're doing is during the suction stage, when your suction valves are open, so charge air basically is basically coming into the thing. The same time this gas valves will open, the signal will go to the magnetic valve and they will open. And in okay, and at 40 degrees and pressure basically varies in this, so 3 bar to goes to about 5 bar depending on the load of the engine. That gas is basically taken. So idea is to mix, okay, this gas LNG basically into the charge air, and you have a homogeneous mixture within the combustion so that it burns. Okay, so that is how it is. So uh, that is how it is. But in Maggie, those basically you have those two things. Now injectors, what you are using over there, you have pilot injectors. There are two tips on those injectors in DFD engines. Okay, one is the main injector, like normal or diesel engines and all you will find, and you have another tip also for pilot injection. The lines are totally different, and the generation is also totally different. You will have normal Bosch type pumps basically for the main injection, and you have a common rail system with pilot fuel pumps having drive from the engine itself. Okay, for the pilot injection with the independent filters and all. That is how for dual fuel engines. Okay. Then Mr. Pinto wants about fire hazards. So if it is, say, see, hydrocarbons are there, so they are prone, and then the fire triangle and all. So you have oxygen, you have the fuel, and you have your heat source. Then fire can occur. Okay, so that is what your fire hazard is all about. So when you're having those, so it is in a gas rich. Okay, you have those diagrams, LEL and lower explosive limit, upper explosive limit. So you either keep it up, so it is gas rich. So even if there is a heat source, there is no combustion happening. So that is basically takes part. Then consumption with ammonia as fuel. See, ammonia still it is in a trial phase with some orders. Engines they have just developed recently and on test bed, and these have been ordered to my knowledge to one major player, methanol player. Sorry, this is what ammonia. Consumption, I honestly don't know. This is something new which is coming in the market. How much it is going to consume, I
See,
have no
the
idea. But density part is
ammonia,
what.
ammonia consumption as you compare to HFO, it is mostly two times more because the ammonia has lower energy
Energy
density.
density.
So
Yeah.
if you use if when we run the engine, two-stroke engine to produce same power and for same distance, the ammonia consumption will be almost 2 point something times more than the HFO. That is what the testing has been done so far.
Okay. Then another question is about ethane carriers come under LNG carriers. See, the as I've said, what determines type of carrier is basically the condition of that particular cargo that you are carrying. And LNG basically works out to minus 161. Ethane works out to about negative 89 degrees. Okay, so both require cooling. Okay, that is the most efficient way to carry. So they are basically fully refrigerated ships. Also, I told you that we can design ships to carry only specific ones. Okay, so they basically come under same type of gas carriers, that is fully refrigerated ones. But commercially, they could be independent. You will have this very large ethane carriers, and you will have a very large. You have LNG carriers. However, having said that, I believe Eagle Star. Okay, the basically Petronas, Malaysian operator, right? So they have ordered and they are operating some ships which are basically designed to carry both. Okay, so you can carry. It is a refrigerated state only, and it is the temperatures that tanks that can handle and the vapor generation that it can handle. So they have come with these ships where, to my knowledge, they are using for ethane, but then they can utilize it to carry LNG also. So that as far as ethane as fuel for propulsion, I'll have to see. I really have no idea about that particular part. Okay, so that is something to be seen. I cannot comment on that. So any more questions, please?
Good evening, sir. Hello.
Yeah.
Am I
Hi,
audible?
good day. Yeah, yeah. Go ahead, please.
Sir, there was a recently accident near the Kandla port, Gujarat. The discharge of methanol. There was an explosion in the ship. What was the major cause of that, sir?
Uh, the investigation, I believe, is quite ongoing, and the conclusion has not come out. To the incident, what you are referring, just for other participants, it discharged cargo and it was just out. They just dropped off the pilot, and then they were just going shifting towards an anchorage wherein there was an explosion in the forward part. Luckily, no seafarer was injured. So there is a fire, of course. So we have to, you say it is something goes to a fire triangle. So explosion has occurred. So they must have not taken some shortcut. Something must have happened. So the investigation will reveal. Most likely DG shipping will come out with something, but then such matters do take some time. The whole investigation and the briefs to come out. This is all I can share about that particular incident to you.
Thank you so much, sir.
Hello, sir.
Yes.
Sir, I have one more doubt. As we discussed, whenever injecting as ammonia as a fuel, will be explosion like each and every injection, right, sir?
Correct. It is basically, it's not smooth. It explodes actually.
Yes, sir. But there are so many R&D are going on still now. But how we can prefer ammonia as a fuel, sir?
See, they are still developing engine and all, test and all are still going on. Okay, so they have to basically control that explosion, and how to control the, basically they will require a pilot fuel injection. So for a longer period of time that the pilot injection is going, so you have a thorough part of it, the geometry, all those things they have to work out. Okay, because you don't want those detonations. You have something known as knocking effect on LNG ships. So you can actually hear tut, 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 there is someone knocking. So they have to control. Okay, so most one thing what I okay, this is not something from the thing, but using our basic knowledge, a longer period of time of pilot injection, so that you have a controlled what I would say, combustion or even injection also. Okay, for a longer duration of time of this ammonia, which is about 80 bar you are injecting, so that you are limiting how much it is going and controlling the whole thing. That is what basically will govern uh, what happens in the combustion chamber.
Sir, sir, it is also a high risk, sir, during leakage and all that. I have sailed already 2 vessels in ammonia carrier, but even it is small leakage also very not acceptable, sir.
Yeah,
But
that is true. That is true. You initially you will have that no bad eggs smell, and then it overpowers, and you won't be able to smell. So it's very, very, very toxic. They will have like what we have seen in this LNG ships. You have concentric pipes, double pipes. Both are pressure rated to the same pressure, with one monitoring and in vacuum. So all those things will be there, and then you have more detectors. The moment something happens, it will cut the
correct.
thing. So let this system come, because they have just tested, and all this proprietary material, until it doesn't come into the mainstream and we read through it and have exposure, cannot really comment much. Okay, we can only
Correct.
imagine based on our past experience.
Yes, sir.
The toxicity and all is there, so there is additional for bunkering also. It becomes much more challenging. Okay, there you will have to have your close EBDs all the time, because
Yes, sir.
I have also sailed on a ship where we were carrying. So normally, if you see a ship which is also carrying ammonia, you will have EBDs in your cabin also. If there is a leak, then
Correct,
you'll
sir.
have to use those to escape from the accommodation
Yes,
to a safe
yes,
space.
sir.
So all those
Correct.
additional precautions will come into the picture, no doubt about it. So
Okay,
let's
sir.
see how they have designed those, how those things basically come into the picture.
Okay, sir. Thank you, sir.
You're welcome.
It
Yeah.
was Chief Engineer Desmond and everybody. It was a very enlightening session here on GMOA webinar series on which we have conducted today. And I thank all the participants, and also Chief Engineer Patson and our IT staff, that is Mr. Amran, and office staff, Ms. Tracy, and GMOA office and the GMOA committee. And I thank Chief Engineer Desmond for his very insightful webinar on the LPG, which was we felt that is the main need in these days of changing technology. Sir, we thank you very much, and we hope we will be able to do more such programs in future. Thank you.
You're welcome. Thank you for the opportunity. Enjoy your evening.
Thank you, Mr. Desmond. Thank you very much. It was very nice.
You're welcome, sir.
Thank you.
Chief Engineer Patson, do you want to say something? Then after that we can
Yeah,
wind up.
first of all, I'd like to thank Desmond Fernandes and for taking this initiative, and also thank to GMO who has given him the platform to conduct this webinar, and also all the guests who has participated in this webinar. Any questions or queries in future, we will share Chief Engineer Desmond number in the WhatsApp groups, so you can have a chat with him. Once again, thank you, everyone.
Yeah. Thank you, sir. Thank you very much. Thank you.
I've just shared my number, so you can just WhatsApp me, okay, and I can revert back to you all. Okay, please avoid calling me because I have like other works and all. So in my free time, then I can take your queries.
Right. Yeah. Thank you, Mr. Ed. Thank you very much.
Welcome. Okay, bye bye. Enjoy, guys.
Yeah. Bye.